Now let's talk about an event. An event is any subset of a sample space. So for example, when an events are usually denoted by capital letters of English alphabet. So for example, we could call event H is getting an even number when rolling a die, right? So event H will be described as follows. An even number is 2, 4, or 6. There are no other even numbers on any side of the die, so this completes our event H. Another example, event J is described as getting a multiple of 4 when rolling a die. So what are the multiples of 4? Well, there is a 4, and the next multiple of 4 is 8, which is not in a sample space of rolling a die. So 4 is the only value in that event. We're going to say that an event occurred if the outcome of the experiment is in the collection that defines the event. So for example, I bet that when rolling a die, I get an even number. So if I got any one of these numbers, event H occurred. If none of these numbers were rolled, then event H did not occur. For example, I roll a die and I get a 3. I'm going to say event H did not occur. I did not win my bet. And we say that an event did not occur if the outcome of the experiment is not in a collection that defines the event. So for example, the event A is described as 2, 4, or 6, basically our even numbers. So if I rolled a die and I got a 1, the event A did not occur. But if I got a 2, the event A occurred. If I rolled a 3, event A did not occur. If I rolled a 4, then the event A occurred. So, and so forth. So that means that not all of these values have to happen at the same time, but if one of these values is happening, then or rolled, then we said that event A occurred. So in order for event B to occur, we should roll either 1, 3, or 5. 1, 3, or 5. In any of those instances, event B occurred. So for event C, it occurs only when we get either 5 or 6. Now, event D, we get 1, 2, 3, 4, 5, or 6. Basically, this is our sample space, right? So when we roll a die, we're bound to get one of these numbers. The die is not gonna freeze in the air. It's not gonna end up on one of the edges, right? We are bound to get one of these numbers. So we're gonna say that event D is inevitable event. Inevitable, meaning it bounds to happen. It's gonna happen 100%. Now event E, this is an empty space, which means nothing is happening. So if we roll a die, what's the probability that we don't get any of the numbers? Well, the probability of that is 0, right? So that is why we're going to call this an impossible event. Impossible event. And the probability of this event is going to be 0. But we're going to talk about probabilities a little bit later. Another definition associated with events is the definition of success and failure. If we're performing a trial and our event occurred, we're going to call it a success. And if we perform a trial in which event did not occur, we call it a failure. If we refer to the previous example, when we rolled a 1, then event A did not occur, that was a failure. But for event B did occur, so it was a success. So 2 was a success for event A, and 3 was a failure for event A. For event B, 2 was a failure, and if 3 was a success. So the words success and failure have no emotional connotation at all. So it just happens that we observed the result that we were looking for. For example, if we're studying monkey behavior and we are looking for display of aggression. So whenever we observe an aggressive behavior, we call it a success, even though it has nothing to do with a success as like we understand it in social settings. Notation that associated with events. Capital P denotes a probability. And as I mentioned before, we denote specific events with capital letters A, B, C, D, E, F, and so forth. So the probability of event A, in this case specifically, we will denote by capital P followed by A in parentheses. We read it a probability of event A occurring. The next concept related to the probability of events is equally likely outcomes and not equally likely outcomes. So for example, when we're tossing a coin, we have 2 equally likely outcomes. So the sample space would be getting heads or tails. That's our sample space. Question, is there a reason to believe that the heads are more likely or less likely than tails? The answer is normally no, unless we get a unfair coin. Now, another example of not equally likely outcomes. An experiment is driving to work, and the sample space would be either getting in the accident or not getting in the accident. That's on the way to work. That's your sample space. And question is there a reason to believe that it is likely to, it is more likely to get in the accident as it is not to get in the accident while driving to work? Well, obviously, these outcomes are not equally likely. Another example of equally likely outcomes is rolling a die. We may get numbers 1 through 6, but getting each number has an equal possibility, right? So question, is there a reason to believe that 1 is more likely to happen than 4, or 6 is more likely than 3, or vice versa? No. So all of these outcomes are equally likely. All the outcomes in a sample space are equally likely, where the sample space, by the way, is 1, 2, 3, 4, 5, or 6. And on the other hand, example for not equally likely outcomes is counting the number of credit cards in someone's wallet. And for sample space, let's list, we could have 0, right? Credit cards 1, 2, 3, 4, or for the last one, of course, theoretically, there could be infinite number of cards in someone's wallet. So we're going to have more than five, or more than 4. We should say 5 or more. Okay, and more than 4 covers that too. Okay, so is there a reason to believe that to have no credit cards is as likely as having 5 or more? Well, I think so. Definitely, there are different outcomes, different possibilities for those outcomes. So here's the thing, we're going to discuss 2 different approaches for calculating probabilities. And when your outcomes are equally likely, then we're going to use classical approach. And when they're not equally likely, then we're going to use empirical approach. Okay, let's go to the next video.